So we have a unit the player can control, and we want to move it from one point of the map to another, preferably by the shortest path possible. We could use the built-in Unity navmesh system, but what if you want to write your own pathfinding algorithm, either because you want to have more control over it or you just want to understand how it works? Well, that's what we're going to be covering today in this video. Hi, my name is Michael and I make content based around game development. Today I'm going to be showing you the breadth first search pathfinding algorithm. This is the second part to my last video where we created our tiles, our units, and we got simple teleporting movement going on. In this video we're going to be going over what breadth first search is, how it works theoretically, how we can implement it into the project from last video, and finally, as with my last video, I will give you this project along with some ideas for things you can do with it. So with that, what is breadth first search? It is an algorithm for searching through tree or graph data structures. In game development, we can use this to find the shortest path between 2 points. It works best in unweighted graphs, which means that there is no cost associated with moving between nodes. For example, imagine a game where you have sandy tiles and grassland tiles and you have movement energy. An unweighted graph would mean that the player can move across these tiles with the same movement cost, whereas a weighted graph would mean that the player would be moving across them for a different cost, say 2 for moving across sand compared to 1 moving across plains. Weighted graphs are better suited to Dijkstra's algorithm or the A-star algorithm. Breadth first search can be used in a weighted graph, it just wouldn't be as efficient. Although, with a few small modifications, you can actually convert breadth first search algorithm into Dijkstra's algorithm, and then with a few more modifications, you can make it into the A-star algorithm, which makes breadth first search an excellent starting point for learning about pathfinding. For those of you who understand Big O notation, breadth first search's order of complexity is OV plus E, where V is the number of vertices, or in our case, nodes, within a graph, and E is the number of edges, or connections between nodes within the graph. Okay, how does it work? We're going to go over to a whiteboard for this, because it's very complicated. I don't need to record this bit. We have a representation of our grid here. As you can see, I've used letters instead of the numbers because it's a lot easier to actually look at. The first thing we have to decide for the algorithm is what order it's going to look at each of the tiles. The algorithm will need to look at all the tiles that are around a given tile. In our case, we'll be looking at the tiles from the top, then the right, then the bottom, then the left. You could just as easily change this so you look at the top, then the bottom, then the left, then the right. You can do any order you want and it will give you a different path. So now we've got that decided, that we'll be looking at our tiles from the top and working clockwise. Now we just need a start point and an end point. So we're starting on A and we want to get to K. It starts at A and it works its way through the map until we get to K. When it reaches K, it knows it's reached its destination, so it ends. Over here is the tree data structure we're going to build to determine our path. And because we're looking at the top tile first, we then look at E, and then we look at the tile to the right, which is B. There is no tile beneath A or to the left of A. We then go to E, we look at I because it's above E, then we look at F because it's to the right of E. Once all of E's neighbours have been looked at, we then jump back to B, so that we're slowly expanding out. We can't look at F because we already explored F, so B only connects to C. Then we just do the whole thing again. I looks up and does M, then looks to the right and sees J. Looks down, we don't need to because we've already done E and there's nothing to the left. F won't need to look up because J has already been looked at, so we only add G to that. And C only gets D added to it. We go up to M and we look at N, which is the only node it can explore. Then we go to J. We can't look at N because we've already looked at it before, and then we look at K and we see we are at our destination. From this we have a path, A, E, I, J, K. Because of the way that trees work, if we were just to run that path, it would actually go from K back to A, so we also need to take that path and reverse it. This will make sure that we travel from A to K using the path of A, E, I, J, K. And that's essentially how breadth first search works. If we wanted to block one of the nodes so that the player couldn't walk on it, we would just tell the algorithm not to include it in this tree, and then it would have to go around it and find a different path. If you want a little activity to maybe get this locked in your head how it works, give me the path from J to D in the comments section below using any orientation, but make sure you tell me the order in which you're looking at the different tiles. We're going to take this whole concept and program it in Unity to hopefully get some of our units moving. So let's go do that. Okie dokie, we are back in Unity. Before we write our pathfinding algorithm, we need to add some variables to node and add a couple of methods to our grid manager. We are in node. We're going to add 4 variables to it. 3 of them balls and 1 of them a node. Walkable will dictate whether we can go onto the node or not. Explored will dictate whether this node has been explored by our algorithm. Path will dictate whether this node is part of the path that is constructed by the algorithm. And the node connected to will also be used by the algorithm for telling us what node it's connected to. Before we go into our grid manager, we need to change our constructor to take in an argument for walkable. And then we just need to say here, this.walkable equals walkable. And that's all we need to do in our node. We're going to jump over to our grid manager where we should have an error down here. This is because we changed the constructor over in node. So now we need to give this the argument for whether it is true or false that the nodes are walkable. Because all tiles when they're added are going to be walkable, we're going to set this to true. Okay, I'm not going to make you watch me write out all these methods because that would take a lot longer, so I'm just going to write them out and then explain them to you. Okay, we got some beautiful methods here, one of which already existed before. The first thing we did was we took the code that was in Awake and we extracted it into its own method called createGrid, which is down here. Now, the first function we made returns a node and is called getNode. We input some coordinates and we get a node at those coordinates if it exists. If it doesn't exist, this will return null and not break the game, hopefully. First thing it does is we make a check to see if the grid contains the key of the coordinates, the node we want to get. If the grid doesn't contain it, we return null. BlockNode method does the same check here to make sure we've got this node in the grid, and then we'll set that grid node's walkable variable to false, which hopefully, if we set it up right, our breadth first search will ignore that node. Our reset nodes method will go through our grid dictionary and set all the nodes as connect to, explored, and path variables to null, false, false. Get coordinates from position and get position from coordinates do exactly what they say. You enter a position and you get the coordinates associated with it back. You enter the coordinates, you get the position associated with them back. And with that, we're ready to start our pathfinding script. So let's jump back into Unity. Right click, create new C# script. What the fuck? Right click, create new C# script and name it pathfinding. Open that bad boy up. Okay, we're going to need a fair amount of variables for this. So first of all, we need start coordinates and a public variable to get those start coordinates. Same again for our target coordinates. We then want 3 nodes, our start node, our target node, and our current node, which is the node that we're currently searching. We need a queue, which will be our frontier. We'll need a dictionary of what nodes we've reached. We'll need our grid manager, and we'll need our grid. And finally, we will need our orientation for which order we are going to be searching the nodes in. So remember earlier in the video when I was talking about the order in which we search the tiles. In the case of our algorithm, we'll be looking at the right first, then the left, then the up, then the down, using the vector to in right, left, up, down, which just simply corresponds to whichever direction. If you wanted this to go in a different order, you would just change the order that the right, left, up, down appears here in this array. So what is the first thing that we want to do in our Pathfinder? Well, we want to get our grid manager, so we want to get our awake method, and we want our grid manager equals find object of type grid manager. If the grid manager is not null, so we have found the grid manager, then grid equals grid manager dot grid. I forgot to make the grid manager grid public. So now our grid is our grid. Okay, so the way we have to program this is a bit complicated and a bit all over the place. And I don't claim to be a king of programming. So I'm going to do a quick cut here and then try to explain all the code to you from top to bottom. Remember, this whole project will be available for download from GitHub in the description below. Right, so let's magic up some code. Here is the code in all of its glory. So we'll start at the top. So the first method is our getNewPath method. It takes in our starting coordinates and then we'll return a list of type node, which is going to be our path. The first thing it does is it tells the grid manager to reset the nodes. It then runs breadth first search with our coordinates and finally returns a built path. Let's jump into what breadth first search method does. So the first thing we do in our breadth first search method is we set our start node to walkable and our target node to walkable. We then clear our frontier and we clear our reached. We then create a new bool is running for when the breadth first search is running. We enqueue our frontier with the node on our start coordinates, so our starting node. We then add that node to our reached dictionary. We jump into a while loop after that, which will keep running as long as the frontier has something in it and the isRunning is set to true. Current node is dequeued from our frontier, so it's taken out. We set the current node explored variable to true. We then run the explore neighbors method until our current node is our target node. At that point, we tell isRunning to set to false, which breaks us out of the loop. When we go into explore neighbors, we build a list of nodes from our neighbors. For each of the 4 directions in search order, we store that neighbor's chords as the current node's chords plus whatever direction it's going in. We check if the grid contains that node, and if it does, we add it to our neighbors. This will prevent us from adding neighbors that don't actually exist, say a tile to the left when you are on the furthest left. We then run another for each method where we look at every neighbor we gathered in this for each method. We do a check to make sure this neighbor hasn't been reached before. We make sure it's walkable. Providing that criteria is met, we will set this neighbor's connecting node to the current node, so it's where it came from. We will add the neighbor node to our reached, and then we'll enqueue the neighbor onto our frontier. So this sets it up to be one of the nodes that will be searched. We then go back up into breadth first search, and this continues running this while loop, taking stuff out of the frontier, putting stuff in the frontier until we reach our destination. Once we reach our target coordinates, breadth first search has finished running, so the next method is the build path method. The first thing we do in build path is declare a list of nodes, which will be our path. We set our current node to the target node. We then add the node to the path and set its path variable to true. We then enter a while loop where as long as the current node that we're looking at has a connected to node, we will continue going through it. Current node equals current node dot connected to. So we're working our way backwards through the path. We keep doing this until we run out of connected to nodes. We have our path as a list, so then we reverse the list and return the path. And that's how you do the breadth first search algorithm and build a path in code. But then how do we use this path? We still got 2 more functions to go over that I've written in this. We have a notify receivers, which is just a simple message that we're sending out to run their recalculate path method. The recalculate path method is going to come up in our unit controller, and doing this is one way to run any method in your game that has the recalculate path as its name. And we have set new destination. It takes the start chords and changes them to the new start coordinates, target chords changes them to the new target coordinates, and basically resets the whole algorithm. So that's a lot of code, and you probably think that we're done, but guess what? We're not. We need to jump over to our unit controller because at the moment we're still doing the thing where we just teleport to the tile, but we need to write some functions in here so it knows how to follow a path, how to get a path, and how to say where it is and where it wants to go. Again, I'll just do a quick cut. Okay, so the changes to unit controller. We got 2 new variables here. We got our path finder and we got our path. And down here where we were doing the movement before, if we hit a unit, it stays the same how it was. But if we hit a tile, we then get the target chords from a new component I'm going to make in a moment, which is going to be stored on each of the tiles. We get the start coordinates from our current position in the world. We run the set new destination method on our pathfinder. We pass in our start coordinates and our target coordinates, which we just declared. And then we set recalculate path to true, which is a new method down here. In recalculate path, we have a bool for resetting the path, which if you'll remember from before, in our pathfinding, we have that message broadcast because we don't want to be necessarily recalculating and resetting the path. The only time we want to reset the path is the first time we do it, which is when we click on where we're going. If we are resetting the path, then we are getting the start coordinates from the pathfinder. Otherwise, we're getting the coordinates from our unit start position. At this point, we stop all coroutines. We clear the path if there is anything in there by accident, and we say that path is pathfinder.getNewPath coordinates. This is us passing in our start coordinates, which then jumps over to our pathfinding script, runs breadth first search, and all those other methods from before. After that's done, we've got our path, we start a coroutine called follow path. In order to declare a coroutine, we start off, instead of doing it as a void method name, whatever, we type in IEnumerator followed by the method name. In this case, IEnumerator follow path, and all this code does is it runs a for loop. All this for loop does is takes our start position and our end position, taken from our selected units position and from the grid manager respectively. We have a float for travel %. This is to create a smooth transition from one point to another. And then we tell our selected unit to look at the end position. It's not really going to matter at the moment because our units are, spheres. But if you had a unit that had a gun or something, they would be facing in the direction they were going. After that, we run a while loop within our for loop while the travel percent is less than 1f, so less than 100%. We're going to increase the travel percent by time.delta time, which is just the Unity way of keeping time, times by our movement speed. This will affect how fast we transition between different nodes. Selected unit.position equals vector3.lerp, start position, end position, and travel percent. I don't really understand maths very well. I'm going to tell you that now. But lerp is essentially a mathematical thing that makes it so that you can easily get from a start position to an end position in a smooth manner. And that is what we're telling it to do here. Yield return new wait for end of frame is just how you end a coroutine. The final thing I'm going to do is create this tile class, which will only take a second. We're going to jump back into Unity and create new C# script and call it tile. And wow, magic code. It's holding its own chords from its position, so that when we click on it, we'll be able to get those chords for our end position. And it's got the grid manager, so it knows how much to divide by when calculating its coordinates. Now, we should be able to just jump back into Unity. Now we're just going to quickly hook all this up. So we're going to jump into our tile prefab and stick tile onto it. We are then going to put our pathfinding script on our unit controller. And I think that should be it. If we hit play, we should be able to click on a unit and they will smoothly transition from one point to another. Let's go. Look at him go. Click on this one, move him over there. I mean, he runs into the ground. They lose half their body, but it works. The final thing we're going to do for this video is block nodes, so that when one unit is standing on the node, it's automatically blocked, so the other unit has to walk around him. We're also going to make it so that a tile can be set to blocked by a simple tick box in the inspector. We don't need to write any scripts for this. We just need to modify what we already have. We're going to add a serialized field for a bool. I'm going to quickly extract this into its own method. We're going to write an if statement that if blocked is true, then it will set the node to be blocked from the start. If blocked, then grid manager dot block node. With chords is the node we're blocking. Now if we save this and jump back into Unity, we click on one of our tiles and we set it to be blocked, and hopefully when we press play, if we click on our unit and click on 3-2, they should go around it. There you go. And like that, 3-1 is being excluded from the tree. So now we could put something on that 3-1, like a building or something, and the unit would have to walk around it. But at the moment, if one unit is in one place and a unit is next to him, he can just walk through the other unit. So we're just going to quickly set it up so it blocks the node the unit is standing on. In order to do that, we just jump into our pathfinding, scroll down to where is running is set to false, and in that we're going to set the current node dot walkable to false. I believe we already set it to true at the start of the algorithm, so if we try that now, we put this unit onto 2-2, we put this unit onto 2-3. Now obviously 2-3 to 2-1 is the shortest path, but this unit's in the way, so will he walk around him? He does. Wonderful! But then if we move him out of the way, can 2-2 then be used? It can be. Wonderful. If we want to block any node from the start, we just go over to here in our inspector and check this little blocked tick box. Before I finish up this video, I've just cleaned up my assets folder, put stuff into different folders. I've also made a change to our labeler script. This change is more to show you the breadth first search in action. I will show you the code in a second. If I hit play, you'll notice that our numbers have disappeared. If I click on a unit and click somewhere else, he still moves to that position. If we then hit the C key on our keyboard, that brings up our numbers again. But now we'll be able to see the breadth first search. I have not chosen very good colors. Over in our prefab for our tile, we've got the colors here. If the node hasn't been looked at yet, if it's blocked, if it's been explored, and if it's part of the path. Okay, so as you can see, 3-1 is blocked because we blocked it earlier by pressing it. If I click on this unit and click over here, it's explored all of these nodes, but this is our path from here to here. If we then click here, we can see that the path would be from 0-0 down to 1-0 to 1-1 to 1-2. It's only explored the nodes that are necessary. All these white nodes haven't been touched. Here is our labeler class with some of the changes that we made. Here are the serialized fields for our colors. If the application is not playing, so we are not playing the game, then the labels are enabled so we can see them in the editor. Otherwise, by default, the labels will be turned off. The player has to press the C key in order to turn them on and off again. Here we set the label color depending on the variables that each node has. There is some priority to this. If a node is not walkable, that obviously takes priority over it being a path, over it being explored. And with that, we have a breadth first search grid-based movement system. That's easily expandable. We can have as many units as we want, and we can make the map as big as we want too. Although there are 2 bugs, and I'm not going to fix them now because this video would get way too long otherwise. One of the bugs, as we already know, when the units move, they decide that they want to clip halfway through the ground. I don't know about you, but that doesn't really seem very healthy to me. And the second one is if we move a unit and then click on the other unit, they'll teleport like this, and it's kinda glitchy. So to fix this bug, you'd have to make it so that the player can't actually click while one of the units is moving. Or you would have to give the pathfinding algorithm to each individual unit so that they have their own pathfinding algorithm to work with rather than all of them working from one, because they're all just working from the unit controller right now. And obviously at the moment it's kind of hard to see where each of the tiles are on the screen here. That could easily be fixed just by going into the tile prefab and adding a border around it. But it is time to now end this video. Well, that's the end of the video. If you want to download this project, you can just go into the description below and click the GitHub link. If you want some things to do with the project, you could fix the bugs that I mentioned earlier, add some kind of AI system, add some kind of turn system, or, you know, just do whatever you want with it. I'd be very interested to see what you do with this. And with that, this is the end of the video. Thank you for watching. I hope you enjoyed it. This is my first video edited in DaVinci Resolve. My previous videos, I was using some really old version of Sony Vegas. And I was kind of forced into using DaVinci because I recorded in the wrong format, so my bad. Well, that's it. Thank you for watching. I hope you have a great day.